Every atom in your body is built around a nucleus, and almost every nucleus is built around one particle, the proton. We teach it as familiar, solid, settled, charge +1, spin 1/2, 3 quarks bound by gluons. But there is one basic question about the proton that sounds almost childish, until you try to answer it. How big is it? Not how much does it weigh, not what is it made of, but the literal size of its electric charge distribution. The radius that tells you how the proton's positive charge is spread out in space. For decades, physicists thought they had that number nailed down. Not approximately, precisely. Then a different kind of hydrogen atom was created, one that should have made the measurement cleaner, sharper, more definitive. Instead, it produced a number that did not match reality as we understood it. And the mismatch wasn't a rounding error. It was a split big enough to force an uncomfortable question. Did we misunderstand the proton, or did we misunderstand the rules that govern electrons and muons? To see why this matters, you need a sense of scale. A proton is so small that normal language fails. The radius we're talking about is on the order of 10 to the power of -15 meters. That's a femtometer, a millionth of a billionth of a meter. If an atom were the size of a football stadium, the proton would be smaller than a dust speck near the center. And yet we try to measure it, because that tiny size subtly shifts the energy levels of atoms, and those energy levels define the colors of light atoms absorb and emit. These are not abstract details. They feed into the most precise tests we have of quantum electrodynamics, the theory that predicts how light and matter interact. For most of the late 20th century, two completely different experimental roads pointed to essentially the same proton radius. Road 1 was electron scattering. You fire a beam of electrons at protons and measure how the electrons deflect. If you do this at many angles and energies, you can reconstruct the proton's electric form factor, basically a mathematical fingerprint of how charge is distributed inside. Then, by extrapolating that behavior down to extremely low momentum transfer, you extract a radius. Road 2 was spectroscopy of ordinary hydrogen. In hydrogen, an electron occupies quantized energy levels. But the electron is not a tiny planet in a clean orbit. It's a quantum wave. In certain states, part of that wave overlaps the region near the proton. If the proton were a perfect point charge, the energy levels would be one thing. If the proton has a finite size, the energy levels shift by a tiny amount. Measure specific transition frequencies with extreme precision, and you can work backward to infer the proton's radius. By the early 2000s, the long-standing value was about 0.88 femtometers. Not because anyone loved that number, but because independent methods had converged there, within the uncertainties of the time. Then came the muon. A muon is essentially a heavy electron. Same charge, same spin. It interacts electromagnetically the same way, at least according to a central principle of the Standard Model called lepton universality. The difference is mass. A muon is about 200 times heavier than an electron, and it is unstable. It decays quickly. That mass changes everything about how it behaves in an atom. Replace the electron in hydrogen with a muon, and the muon's orbit collapses inward. Not metaphorically, quantitatively. Roughly 200 times closer to the proton. That means the muon's wave function overlaps the proton far more strongly. And that is the key idea. If you want to measure the proton's finite size effect, you want the particle feeling the proton to spend more time near it. Muonic hydrogen amplifies the finite size shift dramatically, turning a whisper into a shout. So in 2010, researchers at the Paul Scherrer Institute created muonic hydrogen and measured a laser transition that is exquisitely sensitive to the proton's size. They expected to sharpen the old number. Instead, the extracted radius came out around 0.84 femtometers. That difference, 0.88 versus 0.84, sounds trivial until you translate it into what it means for physics. It isn't the proton got slightly smaller. It's one of two things must be true. Either something about the older methods, electron scattering, hydrogen spectroscopy, or both, was systematically biased in a way that survived decades of scrutiny. Or, two, Muons and electrons are not behaving identically in hydrogen-like atoms, which would point to physics beyond what we currently accept. And the muonic result wasn't marginal. The original discrepancy was reported with extremely high statistical significance. The reaction across physics was immediate because this was not a complicated speculative corner of theory. This was the cleanest arena we have, bound state QED. Suddenly, the proton radius became the proton radius puzzle. If you want to understand why the puzzle was so hard to kill, focus on what each technique is really measuring. Electron scattering measures how electrons interact with the proton's electric structure. But to turn that into a radius, you must do a delicate extrapolation to the limit of zero momentum transfer. That's where model choices and subtle systematics can matter, because you're extracting a slope at a point you can't measure directly. Hydrogen spectroscopy measures transitions influenced by many constants and corrections, including the Rydberg constant, one of the most precisely determined quantities in physics. The proton radius enters as a correction, but it's entangled with other parameters unless you measure specific combinations and multiple transitions. Muonic hydrogen, on the other hand, makes the proton size effect huge, but now you must trust that you understand every QED correction in a regime where the muon is deep in the proton's neighborhood. Tiny theoretical terms that were negligible for ordinary hydrogen can become important. So the scientific world did what it always does when a clean number breaks. It attacked the problem from every direction. New spectroscopy groups measured different hydrogen transitions with new techniques. Electron scattering experiments reworked targets, detectors, and kinematics to push into the low Q-squared region where the radius extraction is most direct. Theoretical teams reanalyzed radiative corrections and two-photon exchange effects that can subtly distort scattering data. And experimentalists started building something that, oddly, had never been done in a decisive way: a direct comparison of muon-proton scattering and electron-proton scattering in the same apparatus, under the same conditions, to test whether muons and electrons truly behave the same way in this context. Now here's where many summaries get this story wrong, because it's tempting to give it a clean ending. It's true that several newer measurements pulled the electron side closer to the smaller muonic radius. In 2019, the PRAD experiment at Jefferson Lab reported a smaller radius from electron scattering, around 0.831 femtometers, closer to the muonic value than to the older 0.88 era consensus. And over the last few years, the overall landscape shifted enough that CODATA's recommended proton charge radius moved to the small neighborhood, about 0.8408 femtometers, consistent with muonic hydrogen. If you stop the story there, it sounds like the puzzle is over. The proton is smaller. The old value was a collective artifact. Everyone goes home. But that is not actually the honest ending, because the puzzle didn't vanish. It changed shape. First, not every ordinary hydrogen spectroscopy result has aligned perfectly. The spectroscopy world has produced a cluster of results with strong weight on the smaller radius, but the broader set has not been a single, perfectly harmonious choir. Second, in scattering, the extracted radius still depends sensitively on how you fit the form factors, which data you include, and how you control systematics at extremely low momentum transfer. There remain analyses and reanalyses that show the radius can drift depending on modeling choices. Exactly the kind of fragile behavior that makes physicists nervous. Third, and this is the big one, if the original drama was muons versus electrons, then the cleanest possible resolution is not a better hydrogen laser, and not a cleverer electron fit. The cleanest resolution is to measure muon-proton scattering directly, with precision good enough to say whether the muon sees a different proton than the electron does. That is the goal of experiments like MUSE, which is designed to scatter both electrons and muons, positive and negative, off protons in the same setup, to test both lepton universality and the radiative corrections that could masquerade as a radius shift. And until results like that fully mature and lock the story down, there's a remaining tension at the philosophical core. Did we uncover a measurement artifact that fooled us for decades? Or did we glimpse a crack where new physics could hide? subtle enough to affect muons differently, but quiet enough to evade every other test. Because that's the thing about the proton radius puzzle. If it were just a bad experiment, it would be boring. If it were just a bad calculation, it would be fixable. But this puzzle sits exactly at the boundary where the most successful theory in science, quantum electrodynamics, meets the messy, composite reality of a proton whose interior is governed by the strong force. You are trying to infer a physical size from an interaction that is mediated by photons, corrected by quantum loops, influenced by nuclear structure, and extracted through extrapolations that rely on mathematical judgment. And in that environment, a difference of 4% is not a rounding error. Because protons aren't just in matter, they define matter's scale. They set the baseline for atomic structure. They sit inside every chemistry textbook and every precision clock and every spectral line we use to measure the universe. So here's the uncomfortable, still open reality. Yes, today's recommended value is in the smaller range, and many newer experiments point that way. But the path to that number exposed how delicately our conclusions depend on the chain of assumptions connecting raw measurements to a radius. And the most decisive test, directly comparing how muons and electrons scatter from protons with the same experimental DNA, is still the kind of result that can either close this story for good or reopen it in a way that no one is ready for. Because if muons really do see the proton differently than electrons, if lepton universality fails even slightly, then the proton radius puzzle would stop being an embarrassing metrology saga and become one of the first clean, laboratory-scale hints that the standard model is incomplete. So the proton remains what it has always been, the anchor of ordinary matter. But its size, this absurdly tiny, supposedly simple number, still carries a question that physics has not completely nailed shut. Is the proton's radius a settled constant we finally measured correctly? Or a warning sign that one of our deepest assumptions about nature's symmetry between particles is quietly wrong? That is where the story stands. And until the last comparisons are done, until the last cross-checks converge, and until muons and electrons are forced to answer the same question under identical conditions, the proton is still holding something back. Veil origins, impossible truths.